All right, so let's get started. So let me sort of just remind you where we are. So last week, for the first time, we relaxed our incentive compatibility guarantee. For weeks and weeks, we'd been focused just on strong guarantees like dominant strategy incentive compatibility, ex-post incentive compatibility. Last week, for the first time, we started talking about Bayes-Nash implementations. So the current set of goals are the following. As usual, we want simple and polytime mechanisms. As usual, we want to have welfare as close to optimal as possible, at least subject to polynomial time for the case of NP-hard welfare maximization problems. And we want mechanisms that are Bayesian incentive compatible for today, or for this lecture. And remember what that means is that means direct revelation mechanisms should form a Bayes-Nash equilibrium. Okay, now to talk about Bayes-Nash equilibrium, there has to be a notion of a prior. So basically when an agent is reasoning about whether or not direct revelation is a good idea or not, so what do they know? They know some common prior distribution, capital F. They're assuming that other bidders' valuations are drawn from that distribution. They know their own valuation, and there are these strategies. Okay, so they know the strategies that everybody are playing. So I don't know other people's valuations, but if I knew their valuations, then I would know their actions. Okay, so in algebra, so what does it mean that direct revelation is a Bayes-Nash equilibrium? It just means that for every bidder I, whatever its valuation VI might be, so whatever its valuation might be, then direct revelation, meaning just reports the true value, should maximize its expected utility. And here the expectation is over the random draws of the other bidders. When I talked about the general Bayes-Nash setup last week, I allowed the prior capital F to be correlated. Until further notice, the distribution is a product distribution. Okay, so until further notice, bidders' valuations are independent, so I don't need to condition on VI when I write V minus I drawn from F minus I. Okay, so again, BIC means that direct revelation, sigma I VI equal VI, should maximize utility. Okay, so the UI, okay, so here I'm assuming that other bidders' valuations are drawn from F minus I, and I'm also assuming that they're doing direct revelation, okay, because it's an equilibrium concept. Maximizes this over everything that bidder I could do, so over all reports BI. Okay? So in other words, you can declare whatever you want, declare whatever BI you want, but under the following assumptions, first of all, other bidders' valuations are drawn from F minus I. Second of all, the other bidders are doing direct revelation. Under those two assumptions, your utility, expected utility, is maximized by just direct revelation. Okay? So that's what a Bayesian incentive compatible mechanism is. All right? And I don't think, we didn't really talk about, so we didn't really talk about concrete examples last week. The point of this lecture is going to be a very sweeping, really very satisfyingly sweeping positive result. Basically saying whenever you can get a computationally efficient approximation algorithm, you can massage it in a way that it becomes a Bayesian incentive compatible mechanism. Okay? So we'll get positive results that are simply impossible for the stronger notions of incentive compatibility. Okay? So what's sort of the coolest thing that could be true? So the Holy Grail would be that we can achieve all three goals whenever we know it's possible to achieve only the last two goals. So whenever you have a polynomial time algorithm, which has some guarantee on the welfare, we'd like to basically get Bayesian incentive compatibility for free. And I'm going to show you how to do that in this lecture. Okay? Very cool. All right, so what's the sort of methodology that we'll use? Well, it's going to be this black box reduction, which I sketched last time. So let me remind you the blueprint of how this works. So there's going to be, we're going to be given an algorithm A, which achieves only 2 and 3. Okay, so you want to think about a canonical case like bidders with submodular valuations, something like that. That's a problem for which we know there are good approximation algorithms, and we totally failed to get a DSIC mechanism outside of the special case of coverage valuations. So that's A. A is something which is not suitable for a mechanism, but has a good approximation ratio. And we want to design this algorithm B. And the way we're going to do this is we're going to pre-process valuations. Okay? So the valuations will first go into initial subroutine. These are going to be resamplers. And so this will somehow basically resample valuations and feed this new valuation profile into the old algorithm. And the algorithm will not be any of the wiser. The algorithm will just treat these resampled valuations as a valuation profile. It will do its thing. And what we want is, even though A is unsuitable for a BIC mechanism, B can be implemented as part of a BIC mechanism. Okay? So the goal here is, given an algorithm A and a prior capital F, construct an algorithm B, which has the form: first you apply resampling, this is a subroutine R, then you apply A, where Ri is a polytime resampler. Okay, mapping valuations to valuations. All right. So that's the high-level plan. Now, for this to give us the sweeping positive result that we want, basically two things should be true. So first of all, the incentive failures possessed by A should go away. Secondly, we should inherit the approximation guarantee of A. Okay, so what's good about A we retain, what's bad about A we get rid of. So primary goals for R. So again, there's going to be one algorithm Ri for each of the n bidders. Okay? So Ri takes I's valuation and spits out a different valuation. So first of all, the composed algorithm R followed by A is BIC implementable. All I mean here is that, by BIC implementable, I just mean, right, so B is basically an allocation rule, right? It takes his input evaluation profile, spits out some allocation. I just mean I can couple it with some payment rule so that allocation payment rule combo is indeed a BIC mechanism. Okay, so that's all I mean by BIC implementable. There exists a suitable payment rule. And then it should be welfare improving, okay? So if I look at the expected welfare of algorithm B, so equivalently, so remember B is just A applied to the resampled valuations. That should be at least as good as if I didn't resample. And remember, we're motivated by the situation where A is a good algorithm. Okay, so we're thinking of this as being very close to the maximum possible welfare. So maybe for every possible valuation profile, A is close to the maximum welfare, or at least maybe on average over the relevant distribution F, the expected welfare is close to optimal. Okay, and the point here is just that whatever guarantee this has, then our massaged algorithm has it as well. Okay. So if we can do these two things, that's great. That basically says this is the technical sense in which BIC will be without loss for approximation algorithms. Okay. Good. All right. So another really important property for making this work is we're going to have each resampler be distribution preserving. Okay? So remember, a resampler R sub I, it takes we're envisioning it taking the actual valuation at bidder I VI and remapping it to some other valuation. Okay, so it gets an input at random, it remaps it, so its output is also random. We would like the distribution over inputs to be exactly the same as the distribution over outputs. That is, we would like the output of the ith resampler to be distributed according to F sub I. Okay, the same distribution from which VI is drawn. Okay? So this is another property we're going to use as sort of a guiding principle for how we're going to come up with these resamplers, these R sub I's. Now we'll kind of see in the proofs why this distribution preservation property is useful. But let me just say about why why we might want it. In fact, it's sort of hard to think about how you'd prove this result without this property. But so basically, in proving the key properties 1 and 2, distribution preservation will allow properties 1 and 2 to decouple across the bidders. Okay, so decouples proof of 1 to across bidders. And so, we'll see this in more detail later, but just, roughly speaking, what's going on. So, if everybody else's distribution stays exactly the same, remember, the BIC implementability condition. When a player I is reasoning about whether or not direct revelation is a good idea, it's only reasoning about other people in as much as we're sort of averaging over V minus I. Okay, so if behind the scenes there's some resampling going on, which leaves the distribution of what I see in variance, then the decision about whether or not something is the best response is also in variance, stays exactly the same. All right, so somehow, if other distributions stay exactly the same, it allows me to handle incentives separately for each of the bidders. That's the intuition for the first part. For the welfare part, well, so we want the expected welfare to only go up. And so if all the distributions are remaining unchanged, then by linear expectation, I can just handle this bidder by bidder. Okay, that's all that matters. That's the we'll return to that precisely later, but that's the gist about why you might want this distribution preservation property as a tool for proving 1 and 2. These are the two things we really care about. Okay? So that's at the high level. So now the rest of this lecture, I want to show you the construction of these RIs, which is pretty nice, actually. Okay? So I gave you a hint at the end of last lecture. Last lecture I talked about the special case of single parameter settings and uniform distributions, just to kind of as a warm-up. So today I really want to talk though about multi-parameter settings. Right? We're really motivated by these combinatorial auctions problems where we just failed to come up with good DSIC mechanisms. So I'm really thinking about like submodular valuations as a motivating problem. So that's multi-parameter, that's not single parameter. Okay? So it was really just a warm-up last lecture. So here's the general setup. So bidder I am, however, going to retain the assumption from last lecture that there's an explicit set of possible valuations that's finite and that's explicitly given. Okay, and that's not that satisfying an assumption, but we're going to need it for today. Okay, so bidder I has a finite set Ti of possible types. So remember, so pretty much in this class, whenever I say type, you should just think valuation. Okay, so type is just the private information known to that agent that you don't know as the designer. Okay, but think valuation. Has a finite set of possible types or valuations. And you should also think about it that we're basically given as input just a list of the possible types and the probabilities of those various types. Okay, so this is the prior. Okay, so remember all of this only makes sense with respect to a prior. I'm assuming it's a product prior, so I only need to know the marginal distributions, right? So the probability for each bidder, what's the probability of VI, and that's just given as a list. Okay. And so what you might want to think about is you might want to think about, like saying submodular valuations. Think about some concrete class that we've talked about how to represent coverage valuations, k-unit demand valuations, something like that. So just imagine we're given like a polynomial length list of succinctly represented valuations of that type, okay, with some probability masses. Okay, so that's what you should think about. Okay, and then also there's some just algorithm, which again we're thinking of as being a good approximation algorithm, which just maps a valuation profile or a type profile to an allocation. Okay. Yeah, so these are numbers that obviously for a fixed I, these are non-negative numbers that sum to 1. Okay. All right. And so again, think of A as either a good approximation algorithm, possibly in the worst case for every valuation profile, or at least on average with respect to the specified prior. Now, I want to proceed for each bidder independently. Okay? Any questions about the setup? Okay. So here's the way I want you to think about this. Okay? So what we're given is we're given an algorithm A where if only people did direct revelation, we'd get great welfare, right? By definition. It's a good approximation algorithm. So if we ran it on the true input, we'd do well. Okay, that's A. The problem is it's not a BIC mechanism. People aren't motivated to do direct revelation. So let's just make a small change. Let's stick with algorithm A. Let's fix a bidder I, and let's just try to correct the incentives for bidder I, okay, by itself. All right. So for every bidder other than I, let's imagine that they do direct revelation, even though it might not be in their best interest. Okay. So let's analyze the world from I's perspective, assuming everyone else does direct revelation. Okay. Really. Looks like something died on the board here. Okay. So first step. So fix bidder I. And in effect, we're basically just assuming that all the other resamplers are the identity, and everybody else is just directly revealing their information, even though they might not be incentivized to. For j not equal to I. Okay. And so the question is just how to incentivize direct revelation for I under these assumptions. All right. Now what do we have under our control? So there's two things we actually need to design. The first thing obviously is the resampler, the RI, but also remember, ultimately this algorithm B, this is just the allocation rule. Ultimately this is going to be embedded in some mechanism. So somewhere, either implicitly or explicitly, we're thinking about designing a payment rule PI as well. Okay? So the question is, how do we design, just for I, the resampler RI and the corresponding payment rule PI so that its expected utility is maximized by direct revelation? So this is something we talked about in the special case at the end of last lecture. So again, the special case, I said, let's just talk about single parameter settings. This was the end of last lecture. And let's just assume the uniform distribution. And the reason I started us with single parameter settings is because we have a very good sense for what's an implementable allocation rule. Right? It's just monotonicity. We talked about that a lot last quarter for DSIC mechanisms. But as we explained last week, it's basically the same story for BIC mechanisms, single parameter. So an allocation rule is implementable, it can be turned into a BIC mechanism if and only if it's monotone. Okay, so if and only if, as you average over all the V minus I's, the amount of stuff you get is only going up as you bid higher. Okay, so we didn't prove it, but the proof is the same, but we talked about, I called it the extended Meyerson's lemma last week. Okay, monotonicity is sufficient, also necessary, but the point was it was sufficient for BIC implementability. Now the whole point of today's lecture is to do things like combinatorial auctions, which are multi-parameter, which means it doesn't make sense to talk about a monotone allocation rule. Okay? There's multiple things you're bidding on. So what does it mean to just bid more? What if you bid more on one thing and less on another? So this is what's a little intimidating, but actually it plays out really nicely in this context. I mean, if you think about it, what are we trying to prove? We're trying to massage algorithm A into a different algorithm, and then we need to argue, okay, and now all of a sudden it's incentive compatible. So we need to think to ourselves, like, what's that part of the proof going to look like, right? Where we write down this proof and says, oh, now we've got it. Now we've got our incentive compatible mechanism. Because again, we don't have Meyerson's lemma. It's not single parameter. Okay, so we need some part of the proof where we argue we've achieved the desired incentive compatibility. Okay, so that's something to watch out for. That said, it's going to fall out quite nicely. We're again going to use basically a matching approach. So in the single parameter setting last week, we drew up a bipartite graph. On the left-hand side was the true type of a bidder. On the right-hand side was a possible resampled type. And we talked about how distribution-preserving resamplings corresponded to perfect matchings in that graph. We also argued that if the allocation rule was already monotone, then the maximum weight matching for the appropriate weights was just the the sort of easy perfect matching from left to right. So you just match the jth smallest valuation with the jth smallest allocation probability. And if you don't have a monotone allocation rule, then if you compute a maximum weight matching, it just automatically uninverts all the inversions in the allocation rule. And that gave us the monotone allocation rule at the end of the day, which gave us the implementable mechanism. So we're still going to use this matching setup. We're still going to look at, now it's going to be basically fractional matchings from true types to resampled types. And so we can't use Meyerson's lemma to argue monotonicity, but what turns out to be cool is the exact same linear programming duality we use to characterize Walrasian equilibria we'll be able to use directly to argue that we're incentive compatible. Okay? So we're basically going to wind up proving it directly, and we're basically going to wind up proving it directly with tools we've already developed. Okay, so that's the good news. So pretty much all the pieces we're about to assemble you've seen in some form before. Okay? All right. So any questions about any of that? If not, I'll sort of set up, the right analog of the matching for this more general setting. Okay. All right, so here's the idea. So remember, we have two things we need to design, all right, if we want to sort of establish incentive compatibility. We need to pick this resampler. Okay, so how do we remap playerized type? And then secondly, if we want, we can also talk explicitly about what the payments are going to be. All right, so the resampling algorithm R, that's going to correspond to a primal linear programming solution, like fractional matchings, and the prices will just fall out of the dual. So in what way are resampling algorithms equivalent to some kind of fractional matching? Okay, it's going to be fractional, what are called sometimes B matchings, which just means that the amount of flow into or out of a node might be something other than 1. This is also called the transshipment problem sometimes. So let me just show you the LP formulation. And it's basically the same as the LP formulations we were talking about for unit demand bidders. A couple of slight differences that we'll discuss, but no big deal. And so again, the graph you should have in mind here is you want to have in mind on the left-hand side, true types, and on the right-hand side, resampled types. And you should think of a resampling algorithm remapping an input valuation Vi to some other output valuation V hat I as like pushing flow from that true type Vi to the resampled type V hat I. Okay, so the probability between the inputs and the outputs is going to correspond to flow in this graph from the left side to the right side. Okay, so let's fill in some details. So first, what are the decision variables? T sub I is the possible types of bidder I. And so basically they're going to correspond to flow variables. So for a choice of a left-hand side and right-hand side node, we're going to have a decision variable S sub t, which is meant to represent the probability that, first of all, the true type of bidder I is S, and then secondly, that gets remapped to T. Okay? So that is the semantics you should have for the decision variable XST in this linear program. Okay? It's the probability that the bidder shows up with type S, and then it's fed to the resampling algorithm that says, yeah, well, for today, let's report you as T to the algorithm A. Okay? Okay, so constraints. All right, so first, for every true type S, let's look at the sum of the XSTs over T. So this is the sum of the outflow on a left-hand side node. So what should that be equal to? For this to make sense, for the semantics to make sense. So looking at this, so XST is the probability that VI equals S and RI of VI equals T. So if we sum this over all possible T's, so we're summing this probability over all possible T's, then what are we left with? That's just the probability that VI equals S, right? And the probability that VI equals S, that's given by the prior, so that should just be the probability that I has type S. So this is going to be Fi of S, okay? So basically, so another way to think about it is you want to think about the initial flow in this graph. You want to think of this one unit of flow, which is probability mass. And that one unit of flow, or sort of initial commodity, is distributed according to the true types according to the prior. Okay, so at a given node S here, it's endowed with FIS units of stuff. Okay, and we want everything to go from the left-hand side to the right-hand side. Okay, so the outgoing flow should also equal FIS. Okay, good. Now the second set of constraints is motivated by our distribution preservation property. So remember, one of our guiding principles is that when we define these randomized algorithms Ri that map types to types, we want the distribution on the output types to be the same as the distribution on the input types. So given that that's what we want, if we fix a resample type, so a right-hand side node, and we look at the sum of the flow going in, or the total probability mass leading to T, what should this be equal to?
Fi of T.
Good, Fi of T, thank you. Okay? And that's just because that, by definition, is the input, is the probability that the true type is T. And we want the probability that the resample type is T to be equal to the probability that the true type is T. Okay? And good, so that's the entire primal, okay? The entire primal linear program. And the claim is that feasible solutions to this linear program are in bijective correspondence to distribution preserving resampling algorithms, okay? Namely, so how would you define an algorithm from one of these LP solutions? Well, if someone with true type S shows up, you would just output a type with probability proportional to the XSTs, where T's, I'm ranging over all possible output types T, okay? So the probability, given that you have somebody with S, the probability of the output T is just going to be XST normalized by Fi of S, okay? So you want to think of probability that RIS equal T given S. This is just going to be XST over Fi of S. Okay? So that's how, given these X's, you would define the RI. Okay? You just output. So it's basically just, it's almost like a randomized rounding of this linear program, if you like. Okay? On the fly. Okay, good. Is everyone clear on that? Feasible solutions to this are exactly the same thing as distribution preserving random resampling algorithms. Not clear this was helpful, okay, but I just want to make sure the bijection is clear. Okay, but it turns out it is helpful. It's really helpful, actually. Okay, so let's see why. So one question is, is there something that makes sense to optimize over this polytope? Okay, and there is. So in the same way, one thing I want to point out, so even though we'll be using exactly the same math, the exact same complementary slackness conditions we used for unit demand bidders, but the semantics are pretty different. It's maybe like worth squinting and just not worrying about the differences in semantics for this lecture, because it might get confusing. That said, back a couple weeks ago when we were talking about unit demand bidders and the LP duality, we had different bidders on the left-hand side and various items on the right-hand side. Okay? And the edges were kind of the value of a given bidder for a given item. All right? And so now we've fixed a single bidder, and we're just looking at all of the possible roles it might play. Okay, so these are kind of like possible lives that bidder I might be leading, and then the items are somehow corresponding to particular misrepresentations of that bidder designed to kind of coax some algorithm into a better solution. Okay? So the semantics of what things mean is not well preserved, okay? But it's the same linear program, the same duality, the same complementary slackness, and it's exactly what we need. Okay? Okay, good. So here's the objective we're going to want to study. Okay? So let me just write it down, and then as time proceeds, we'll see why it's natural. So, I mean, in the same sense, in the same way, with unit demand bidders, we wanted to do a welfare maximizing allocation. Here, we somehow want to like maximize welfare on behalf of bidder I in some sense. So let me write down the objective for that. So I'm going to maximize over all edges, if you like, so choices of a left-hand side node S, a right-hand side node T. And we're going to look at, the amount of flow going from S to T. And so what's the coefficient? Okay, so there's going to be some edge weight. I need to tell you what WST is. So WST is defined as, it says, well, I's true type is S. We're thinking about the case where, right, so this says true type S, resampled or misreported type T. So imagine that, I's true type is S, but it says that its type is T to the algorithm, and everybody else reports truthfully. Okay? So this is a valuation profile. The other bidders do whatever they're doing. I says its value is T, its true value is S, and I average this over the other bidders. Okay? So WST, which sort of matches up with these semantics, right? So, if you think about this resampling algorithm, an XST pair, that's how frequently somebody with true type S gets remapped to somebody with type T, and then that gets fit into the algorithm. And what we're saying here is just like, oh, well, when the true type is S, and it is actually misreported as T, how good is that for this bidder? Is that like a lot of expected utility or not so much? Expected welfare, excuse me, or not so much, all right? So as always, we use its true type to evaluate its value, but of course the mechanism isn't privy to the true type, it only goes on what it's told, and with this ST pair, algorithm A is being told that the type is T, okay? So this is how good this particular misreport is for this particular bidder, averaging over the valuations for all the other bidders, okay? So if you think about it, that's a sensible coefficient, given our semantics, that XST is how frequently you lie about someone whose S is actually being T. Okay? This is just how good that is for that bidder. Now, why would we want to maximize this? Well, there's sort of two reasons. So remember what our goals are, right? So we have this algorithm A. It's not incentive compatible, but it's a good approximation. So first of all, okay, so we're trying to go towards something which is incentive compatible, and this is going to be vague, but I hope by now you have this sense that incentive compatible mechanisms always are basically optimizing on behalf of the participants, right? Why would you tell somebody what you really want? Well, you'd only do it if they actually, act in your best interests. Okay, if they don't act in your best interests, you're going to misreport your interests. So incentive compatibility somehow has the flavor of optimizing exactly on behalf of participants. And so that's what this objective is doing informally. Okay, this is just saying, given that we're going to remap I's types in some way, let's make sure it gets the most expected utility possible over all possible remappings, okay, given that we're feeding it into algorithm A. That's the first thing. Secondly, the second property we want is we want welfare to only go up. And so at least from bidder I's perspective, again, we're sort of maximizing overall remaps, okay, all distribution preserving remaps, but still, there's this spirit of we're trying to make I's welfare as high as possible. And so that should somehow also lead to kind of us doing only better than we were doing before. Okay, so those are all the reasons this should feel like kind of the sensible objective to write down. Okay? Okay? Good. So, let me just make an informal claim, which basically is just that, for this linear program, so notice, this is the same objective as we had for our welfare maximization back with unit demand bidders. Okay, we've seen this objective before. I'm just going to claim basically we know everything we could care to know about this linear program. Okay, we know it's dual, we know the complementary slackness, etc. Okay, we already did all that back in lecture 6, I think it was. Same LP as for unit demand bidders in lecture number 6. Okay, so there's, aside from the semantics, which as we already discussed are quite different, there's two minor technical differences, let me just point out. So minor technical difference number one is that with unit demand bidders, we had ones here, saying in that case that, okay, I guess two things. So first of all, we didn't have equality. We had at most, okay? Because we were thinking about a case where we had n bidders, m goods, n could be bigger than m or vice versa. So maybe some goods are unsold, maybe some bidders don't get an item. So that makes almost no difference. It just means that in the dual, instead of having non-negative dual variables corresponding to constraints, we have unrestricted dual variables. Okay, that's all. All right, so the equations. Also, the right-hand side was a little different before. We had a 1 here, saying that every bidder should get at most one item, because it was unit demand. That was sensible. And here we had a 1 saying every good should be allocated only once. Okay? Which was also sensible. Here, instead, we have these kind of fractional things. But if you think about it, it's basically the same thing, right? So, like imagine, for example, all of these are multiples of 1 over 100, okay? And so maybe one of these is like 17 over 100, okay? So just make 17 copies of this guy, okay? Each with like 1 over 100. So first of all, I guess, if all of these were the same, imagine it was a uniform distribution. Imagine these were all 1 over 100. Then it's clearly just the matching LP kind of scaled. Okay, it's just a change in units. And if these are different numbers, you could just imagine, looking at the lowest common denominator, or sort of the least common multiple, and just making suitable replicas of everybody, and then just doing matching with the replicas. Matching with the replicas is just going to correspond to fractional solutions over here. Okay? So that's sort of a vague, but just intuitively, this is really going to be the same. Okay? All right. So that's the hand waving that I'm not going to, again, go through the same old duality for this. I'm just going to use it, but there's not really going to be any surprises. So in particular, what we're going to really find useful is the complementary slackness conditions. Okay? So remember what complementary slackness is. So if I give you a solution which is feasible for the primal, I give you a solution which is feasible for the dual, complementary slackness is a necessary and sufficient condition that they're both optimal. Okay? If complementary slackness is satisfied, they're both optimal. If it's not satisfied, at least one of them is not optimal. So let's consider an optimal pair and invoke complementary slackness. So let X star and Y star P star be an opt primal dual pair. Okay, so X star, of course, is exactly what you see here. I'm not going to write it down, but let me just sort of remind you the structure of the dual from before. So there's going to be a set of dual variables for this first set of constraints. So we're going to be calling these the US's. Actually, these won't play any role. And then there's another set for these, the PTs. Okay? These are the constraints have exactly the same flavor as for unit demand bidders, so the dual variables are exactly the same. Only difference, because these are equations, these could be positive or negative. Okay, so in the last application, these were non-negative. Now they could be either, doesn't matter. Okay, so that's why I write U star P star for an optimal dual solution. Okay, U's for these constraints, P's for these constraints. All right, so by virtue of being both optimal for the primal and dual, complementary slackness conditions hold. What do they say? Well, so in the case of unit demand bidders, you might recall what it said, and so this is when we were making the connection to laws and equilibria. Complementary slackness said the only way that a given bidder I gets some item J is if that item J is one of its favorites at the current prices. Okay, by favorites, I just mean utility maximizing Vij minus Pj. Okay, so that's what complementary slackness said back then with unit demand bidders. So now again, the analog is, right, instead of bidders, we have true types, and instead of items, we have these resampled types. So rather than a bidder getting only their favorite items, now it's going to be a true type only gets remapped to its favorite possible resampled types, okay, at the current prices, okay. So complementary slackness will now say, The only reason you would ever have a strictly positive primal variable, x star st greater than 0, is if the corresponding dual constraint is tight. So again, with unit demand bidders, the corresponding dual constraint being tight just meant it was a utility maximizing item for that bidder at the current prices. So here it just means it's a utility maximizing resampled type for this true type at these prices. Okay? So let me write that down. So the only way this could be positive is if what you're getting sent to, this resampled type T, has to be utility maximizing. Okay, so in the argmax, over all possible things you could be remapped to, of your value minus the price. Okay, so the value, remember, in this LP, that's these weights, these WSTs. Okay, so these are playing the role of the values Vij in the unit demand setup. Okay, so we have WSZ minus P star Z. Okay? So again, we could do the derivation, but the derivation is exactly the same as a few weeks ago. Okay, so I'm just going to explain by analogy. All right? So a few weeks ago, we had a Vij and a Pj. Okay? And that was the only difference. All right? Now, we actually had, you might be a little confused how a few weeks ago with unit demand bidders, we actually had 3 complementary slackness conditions, all of which were important. But 2 of those complementary slackness conditions have gone away because now we have dual variables which are unrestricted. Okay, so we also had 2 conditions, one saying, you know, the only reason that a price of a good is positive if it's sold, and the only reason that the utility of bidder was positive is if it gets some good. Those have gone away, okay, basically because we have the equations instead of the inequalities in the primal. So this is the only complementary slackness condition, okay? So if ever you have a primal and dual feasible solution satisfying this, they're optimal and conversely, and it's the converse direction we're using here, okay? So any questions about this? All right, so let's remember what we're trying to do, okay? So we're focused on some bidder I and we're trying to get the incentives correct, okay? And so what I'm doing as a high level, I'm basically saying the way I'm going to get the incentives correct for this bidder, again, I'm designing 2 things simultaneously, how I resample its value and what prices I charge it. I'm computing both at once. I'm solving a primal dual pair, and I'm going to use the primal solution to define the algorithm R sub I. I'm going to use the dual solution to define the payments P. And the reason it's going to be incentive compatible is exactly because of this complementary slackness condition. Okay, so that's how the threads are coming together. Okay, so let me just go back to filling in the details. Right. So, to get Bayesian incentive compatible, so what is R, or R sub I, and what are the prices? So define Ri just by the probability that Ri, so basically again, if the true type is S, you just resample the type proportional to the X star STs, meaning this. Remember the sum of the X star STs summed over T, the sums to F of S, so I have to divide by F of S to get a probability distribution. So that's Ri, and then define a payment rule, PI, such that the expected payment that bidder I has to pay when it declares T, and the expectation as usual is over other people's reports, this should be equal to P star T for all T, okay? So this I hope is clear. We sort of already talked about how the primal solutions correspond to potential resampling algorithms that preserve the distribution. So just to remind you a couple of things about payment rules in a Bayesian setup. So a payment rule by definition takes as input a full valuation profile. Okay, so this is both whatever I reports, whatever it reports T. This is, what the other people report, assuming they're reporting truthfully, so V minus I. This gives me a payment for bidder I on this valuation profile. But again, remember, we're in this regime of assuming risk-neutral bidders. So the only thing I as a bidder care about is my expected payment, where the expectation is over possibly random choices of the mechanism, and then also over the randomness in other people's types. So I actually don't care what this payment rule is, as long as the expected payment by I when it declares T is exactly what the dual linear program is telling me it should be P star T. Okay, so this is just some number like 10. I don't care what these numbers are as long as they average to 10, and neither does the bidder. Okay? So choose PI however you want as long as this equation holds. And obviously, if you want, it could even be sort of, it's easy to think of rules that could do that, many rules that could do that. And I'm agnostic as to which one you do, okay? So this is the construction, okay? So the claim is, if I resample I's truthful declaration according to this R sub I, and if I charge it a price according to its declaration according to this, then at least for I, it is Bayesian set compatible. That is, I maximizes its expected utility if it does direct revelation. Okay? So the reason is already on the board, but let me just, I want to go through it carefully, okay? Because I know there's a lot to keep track of. All right? Okay. Questions?
Ti has to be polynomial.
Say it again?
So the size of Ti has to be polynomial.
Yeah, so right, so excellent point. So the question was about the size of TI, the size of the type space. I mean, at the end of the day, just even trying to run R sub I, right? So even just, I'm thinking of R sub I as literally just sort of, right. So so this linear program is indexed by the types. So the running time of the BIC mechanism we get at the end of the day is going to depend on the type space, which is a drawback. It's probably the biggest drawback of this reduction. And so it's an excellent comment. It's not really clear how you'd bypass that with some general black box reduction. Maybe for specific cases, you could handle implicitly defined type spaces. But just to make sure the point is clear about why it can be a bummer to depend on the type space. So like imagine, right, so it's combinatorial auctions, right, multi-parameter mechanisms. So imagine there's like M goods. Imagine there's like 100 goods, okay? And your value for each of the 100 goods, let's even say you have an additive valuation, okay? So it's like a trivial type of valuation. And for each item, right, you have value either 0 or 1 for that item, 50-50. Independent for the different 100 items, okay? So the number of different types you could have is 2 to the 100, okay? But it was somehow a very simple sounding, succinct to describe, type distribution, all right? So the running time of this thing would be polynomial in that 2 to the 100, okay? Now maybe for, so I think an interesting research question is for sort of nice, implicitly defined distributions, can you have a reduction which then is polynomial in the description size? And I haven't seen too much work on that. I think that's largely open. And if you wanted something as sweeping as what we're doing right now, I'm not really sure how you'd bypass the dependence on the types. So, but yeah, it's an excellent comment. Another way of saying it is the algorithm A that we're given, the good approximation algorithm, we're thinking of that as being polynomial probably only in parameters like n. But then we're going to give a mechanism which is polynomial both in n and in the type space size. So that's the real cost of the reduction. Yeah. Other questions? Okay. All right, so why is this true? So the claim is this is the panacea right here. Okay? Use this R sub I, use this P sub I, and we're good to go. So let's prove that. All right, so key points. So by complementary slackness, whatever I's true type may be, S, basically the resampling algorithm is doing right by bidder I. Okay? So if I look at the various misreported types T that S might get mapped to, all of them maximize I's expected utility. Okay. So R sub I. So remember this. So this is something random. Okay, in general, right? So this is RI is a randomized algorithm in general, but everything in its support is good for bidder I. Okay, so it mixes only over declarations T that maximize I's expected utility, where as usual the expectation is over other bidders' valuations. What is I's utility? Well, again, we look at its true type. The algorithm, though, is run with the declared type and everybody else's true types. And then there's some payment. Okay, so just to make sure this is clear, what's inside the square brackets is I's utility, given that its true type is S, given that the report T is fed into the algorithm A, and given that the other bidders fed their valuations V minus I into the mechanism. Okay, so this is utility. All right. Again, true type is S, but T gets fed into the mechanism A, to the algorithm A. This here, or at least once you apply the expectation to it, right, that is just how we defined the coefficients of our linear program. Okay, we defined it to be the welfare that a bidder with true type S enjoys on average when T is instead fed into the mechanism. So this is equal to WST. And then this, just by the definition of our payment rule, is equal to P star of T. Okay? And so what does complementary slackness say? Complementary slackness says the only way X star ST can be strictly positive, in other words, the only way that the resampling algorithm might conceivably output the declaration T. Right? So the support of this resampling algorithm is exactly the T's for which this is positive. The only way that can happen is if that happens to be a declaration which maximizes, WSZ minus P star Z over all Z's, i.e. maximizes bidder I's utility when it has true valuation S over all possible supports. Okay? So why does that imply Bayesian incentive compatibility? Well, imagine you're bidder I. Right, and you're sort of trying to craft some very clever deviation, some very clever thing. Right, at the end of the day, right, what do? You report some possibly false valuation. That gets remapped to some other report. That gets fed into the algorithm A, and by assumption, the other bidders are just feeding in truthfully their V minus I. That's all you can do. All you can do is influence what at the end of the day gets fed into the algorithm A. Right? The resampling algorithm RI is already feeding it in an optimal response for you every single time with probability 1. Okay? Nothing you can do better than what the resampling algorithm is doing for you. Okay? It only uses best possible declarations feeding into the algorithm A. Okay? So, if we define RI and PI this way, direct revelation optimal, again in the sense of utility maximizing, optimal for I. Okay? Is that clear? So that's really kind of the biggest point of the lecture right there. Right? All right. So you design the resampling algorithm and the payment rule simultaneously as a primal dual pair. Complementary slackness gives you the desired incentive compatibility guarantee. Right. So this is how we manage to kind of dodge basically needing to prove some analog of Meyerson's lemma. We kind of just get the incentive compatibility, we just prove it directly as a consequence of this complementary slackness. Okay, so let me remind you at the outset, I kind of said this was the first step where we made an unreasonable assumption. where we said, let's just focus on a single bidder I. Okay? For all the j not equal to I, let's assume that there's no resampling, and let's assume that even though the incentives are wrong, they just declare their true type. Okay? All the analysis thus far has made those two assumptions. The other RJs are identity, and everybody else is doing direct revelation. But here's the point. What we just said about I maximizing its expected utility by just doing direct revelation, this is still true if we use any distribution preserving RJs, resampling algorithms. Okay? So these should be independent resampling algorithms. But so suppose now, I mean, the point is basically, if I'm bidder I, and I'm doing all my, again, when I reason about whether direct revelation is a good idea or not, the only thing I care about the other people is the distribution by which the V minus i's show up. Okay? All I care about is my expected utility, and this depends on other people's actions only in as much as it depends on the distribution over V minus i's. So if every bidder J, other than me, right? So if they truthfully reveal something, and then they get a randomly remapped declaration, but the distribution is exactly the same as before. So in other words, if each marginal of the distribution over valuations is the same as before, what do I care? Okay? So before, this was the best thing for me, assuming averaging V minus i's according to F minus i's. Now there's from my perspective, it's basically like you swapped out one algorithm that had a particular output distribution. You swapped in a different algorithm with different code with an identical output distribution, and you asked me if I care. Okay? And by assumption, with these risk-neutral bidders in this Bayes-Nash setup, I only care about my expected utility with respect to the distribution over F minus I. So any changes you make that don't change that F minus I, don't change what I think is the best response or not. Okay? So initially we thought about RGAs being the identity, but it doesn't matter. As long as they preserve the distribution, direct revelation is still the best response for me as bidder I. Okay? Because all I care about is maximizing this, and again, this quantity only depends on other bidders in as much as it depends on the distribution over V minus i's. Okay, so the reason is that F minus I is unchanged. Okay? So again, before we were making two assumptions. First, that the RJs were the identity, and secondly, that people were doing direct revelation, okay, even though they didn't have an incentive to. Now, we're not assuming that the other RJs are the identity. We're just assuming that they preserve the distribution, but we are still assuming that the other bidders do direct revelation. But now that's okay, because they also, by construction of their RJs, maximize expected utility by doing direct revelation. Okay, so it's a Bayes-Nash equilibrium. It's only a best response for me if you're also doing it. That's the normal equilibrium concept. Okay, so I should do direct revelation as long as you're doing direct revelation, but that's fine. We get that simultaneously for all of the bidders. Okay? All right, so in other words, so as long as we define all RIs and PIs this way, and by this way I just mean you solve this separate primal dual pair for each of the bidders to get the corresponding primal RI, dual PI. Then we indeed have our desired BIC mechanism. Okay. So next up is the welfare analysis, which is not hard. But any questions before that? Any questions just about how we got the incentives right?
Did you really need distribution preserving here?
Well, okay, yeah, so what could go wrong? So it's conceivable there's some other construction that doesn't require it. But the obvious problem would be, right, so I mean, I need to, right, so I care about what V minus I is being fed into here, right? So my utility for both of these, right? And so, sometimes this number is going to be high, sometimes this number is going to be low. And depending on what I declare, it's going to change, right? And so like imagine you have imagine there's two things you could declare, right? And, and in each case, there's a case where you get high utility, and there's a case where you get low utility. And you're wondering, what should I do, option A or option B? Well, whichever one is more likely to give me high utility, that's my best response. But the point is, if I change the distribution over the v minus i's, right, now it might be the case that, now all of a sudden option B is more likely to give me high utility than low utility. Because of course my utility depends on other people's reports. So it seems like you'd need some more global construction if you wound up not preserving the distribution of every single bidder. So I guess a different way I'd put it is, if you have in your mind that you want a black box reduction and you say to yourself, how could I possibly prove it? I think this is the first thing you'd want to try. And the cool thing is that it works. Yeah. I mean, the other thing you could try to do is you could try to somehow do it iteratively. You could try to sort of like first fix bidder 1, assume bidders 2 through n, assume, deal with them later, and correct bidder 1, and maybe you screw up the distribution. And then you proceed to bidder 2, and you could try to do it for it. But then the problem is, by the time you get to the end, maybe you've screwed up bidder 1's incentives again. So hard for me to see how you do it without the distribution preservation property.
So I was just thinking, as long as everyone's posterior is the same, you could just condition on whatever that posterior is. You lose your welfare, but that.
Say it again?
As long as the.
So you're saying imagine I now have a correlated F.
No, not correlated. It's independent for each person. And just making sure the same independent thing for each person. The same independent mapping for each person. You just care what the distribution on the right-hand side of your matching is in this.
Yeah, I'm not so sure, right? Because the weights, if you look at the...
Weights change. Yeah, so the weight should be with respect to whatever you've engineered the posterior to be. It has no use, but...
Right, but you better be optimal with respect to the real weights. Maybe we can talk about it more later. So, yeah. Okay. Other questions for the welfare analysis? Okay. All right, so we've got the incentive property, so that's good. So welfare analysis. And so again, we can just do this bidder by bidder. Right, so by linearity of expectations, we can just look at, we're actually going to argue that each bidder's contribution only goes up. So let's start with the contribution of a bidder I to the expected welfare in the mechanism. Okay, so after we've done the resampling. Okay, so we're averaging over all inputs, so the entire valuation profile. And we want to look at the overall welfare, where what's being fed into the algorithm is so this is just expected welfare of B, okay? This is what we want to argue is high, has only gone up. Okay, so, well, what is it by definition? So for bidder I, well, there's the various types it could have. Okay, so let's just condition out on what its true type S is. Now let's examine what the resampling algorithm does to its type. So this is just sum over T, and this is just the probability that Ri of S is equal to T. And so what is this? Right, so by construction, this is just whatever the linear program told us it should be, normalized to be a probability distribution. Okay, so this is just X star ST over F of S. So of course we get some happy cancellation there. And then there's still some randomness left. Right, so what we've done is we've conditioned on what I's true type is, what type it's reported to the mechanism A, and then we have the expected welfare, where the expectation is over the remaining randomness, which is over the remaining valuations of other bidders. And this is, let's see, so I's true type is S, and then again the algorithm is invoked with the resampled actually, I guess I've conditioned on t. So, sorry, t v minus I. So I've cheated a little bit here, right? Really what I should write here is the resampled version of v minus I. But the point is, it doesn't matter for this expectation, right? If I take the expectation over v minus I or take the expectation over r minus I, v minus I, same distribution. Okay, it's the same number. Okay. So this is again where we use the distribution preservation property, the resampling algorithms. Okay, so we have a name for this, right? So this is just our linear program coefficients, right? Expected utility to a bidder when its true type is S and T gets declared to the mechanism. Okay. So all this becomes sum over ST, X star, ST, WST. Okay. Which makes us happy, because this is exactly what we explicitly optimized in our linear program. So that sounds promising. So that's I's contribution to the welfare in B. What about I's contribution to the welfare of the original mechanism? So this was to B. Okay, so this is now, oh yeah, I see. Right. So contribution to, right, blah, blah. So without the resamples. So this, again, we can condition on what bidder I's true type is. That happens with S occurs probability Fi of S. And then S is what actually gets fed into the algorithm. So this is just going to be S A S V minus I. So this, again, this is just, this is one special case of the coefficients in a linear program. So this is just the expected utility to bidder I when it actually has a true type S and declares it, also known as WSS. And the point is, okay, so the welfare after resampling corresponds to the optimal solution of a linear program. And the claim is just that our old welfare was some feasible solution to this linear program. Okay, and therefore is at most as good. Specifically, we can think of this, right, so these are the WSS's. So this is as if we take our usual objective function and all the terms are 0 unless t equals s, in which case x hat is just equal to the full mass Fi of s. Okay. And the point is, this is a feasible solution to the LP. And X star was chosen to maximize the objective, so new is at least old. All right. Which is what we wanted. Okay? So that's the welfare analysis. So, you know, basically what one would really hope would be true is true, right? So we know that there's, we know from things like the VCG mechanism that there's really good coincidence between getting the incentives right and getting optimization right, and we see that here. So basically we define the random sampling algorithms and the prices from optimization. It only improves the welfare. Again, the intuition is the same as a single parameter case. Somehow in optimizing the weights, you just sort of uninvert all of the inversions in the allocation rule you were given with, and you get the incentives for free. So let me just say where this algorithm is from. So there were 2 concurrent SOTA 11 papers. So one by Bui and Ji Wang, who's actually at Stanford as a postdoc these days. And then the other paper was by Jason Hartline, Bobby Kleinberg, and Maleklian. So that's where these come from. Okay? And so what we can conclude, there's definitely some technical fine print, and the biggest point is what we mentioned in the discussion, which is to, basically even sort of writing down these sampling distributions is polynomial in the type space, and that's undesirable in some contexts. But so it says you can take any polynomial time alpha approximation algorithm, polynomial in whatever, and there exists a BIC mechanism, which is polynomial in the same stuff plus polynomial in the number of types, which has just as good an approximation factor in as BIC. So again, like a killer application, think submodular valuations. We mentioned in passing that if you throw out incentives, you can get 63%, maximizing welfare with submodular valuations. DSIC, have no idea. Okay? We gave one for coverage valuations, but in general, it seems like one might not even exist. Okay? But this says if you relax to BIC, you can get that 63%. Okay? So the mechanisms aren't that simple. That's the point of the next lecture, starting with the next lecture. But in principle, this really kind of shows how much, how much easier, in some sense, the sweeping positive results you get with Bayesian incentive compatibility that you don't with DSIC. All right? So I'll see you in about 10 minutes, and then we'll kick